Hello, welcome back to the channel. In this video, I'm going to discuss Cambridge IGCSE Physics Paper 4 Theory Extended Paper, February March 2024, Paper 42. Let us get started. Look at the first question, number 1A. Fig 1.1 is a speed time graph for the first 5 minutes of a bus journey. Describe the motion. Motion means movement. You have to remember that. Between first one, t equals to 0.9 minutes and t equals to 2.9 minutes. Now I have to determine 0.9 is somewhere here. This is 0.9 minutes and 2.9 is somewhere here. 2.9. So what is the motion here? Let me draw a straight line first up here to see what is this. Okay, it is within this line here. So I would like to draw a straight vertical line. So I'm going to use the highlighter to highlight. This is the motion, right, that I have to discuss within that given time, 0.9 minute to 2.9 minute. So when you see this is a horizontal line here, and this is a speed time graph, horizontal line, that means the speed of the bus remains constant. Don't you think so? It is constant at this value of the speed. So I would say that the bus is moving at constant speed. Yes, exactly. Now, the second part, t equal to 2.9 minute and t equals to 3.5 minutes. 3.1, 3.2, 3.3, 3.4, 3.5 is somewhere here. So this is 3.5 minutes. I'm going to use the different highlighter here. So this one. So it is the line, the slanting line that I highlighted with green color. So you can see that the speed decreases to 0. But when you look at this graph, this is a speed time graph, right? From when a graph is being given, you have to bear in mind two information here. There are two information that we could obtain from the graph. From the speed time graph, the gradient of the graph represents acceleration. So you could also talk about the acceleration, and the area under the graph represents the distance. Now, in this case, because the question asks us to talk about the motion, so it has nothing to do with the distance. Right, you can talk about the accelerations. This is a straight line graph and it is slanting downwards. You will have a negative gradient. Negative gradient represents the speed that is decreasing constantly. Right, so when the speed is decreasing constantly, the gradient of the graph represents acceleration. Therefore, the acceleration is constant, the constant deceleration. So I would say, okay, constant deceleration. If you don't like the word constant deceleration, you could always replace it with speed decreases constantly or uniformly, right? Not a problem. Now, t equals to 3.5 minutes and t equal to 4.5 minutes. 4.5 is somewhere here. So I'm going to use the different highlighter here. 3.5 to 4.5. Oh, the time is moving, but the speed is equal to 0. So I would say that the object is not moving. Or the bus is at rest. The bus is stationary. That's it. Now, B, another bus travels at a speed of 8.9 meter per second. The brakes apply a constant force and the bus stops in a distance of 23 meter. This bus has a mass of 18,000 kilograms. Wow, a heavy bus, don't you think so? First part, calculate the kinetic energy of the bus before the brakes are applied. Kinetic energy is the energy related to motion. So do you still recall the equation of kinetic energy? Let me give you. So I'm going to put EK represents kinetic energy. It is half mv squared. Half mass of the bus is 18,000. V is the speed of the bus, which is 8.9 squared. Because the bus is moving at 8.9 meter per second before the brakes are being applied. Therefore, okay, here I got 7.13 times 10 to the power of 5 joules. That is the answer of the kinetic energy. That's the value of the kinetic energy. Now you have to bear in mind before you fill in the blank for the kinetic energy, make sure that you rounded off your answer to 2 to 3 significant figures. You can put 7.1 times 10 to the power 5 joules or 7.13, which is 3 significant figures, times 10 to the power 5 joules. And the unit of kinetic energy is in joules. Right. Now the second part, calculate the force applied to bus, to stop the bus. When I have already calculated kinetic energy, the other clue for you is that whenever you see that the first part that you have calculated, the second part is normally related to the first part. Now, I'm going to use this. I said that kinetic energy, EK, is an example, is one kind of energy, and I could relate the kinetic energy to work. Why? Because the definition of energy, the definition of the general energy is the ability to do work. Whenever you have ability to do work, you have the energy. So work is equivalent to energy, which is equal to force multiplied by the distance. Okay, I put FD, distance. Work is in terms of energy, kinetic energy, which is 7.13 times 10 to the power of 5. Force I have to find, multiply by the distance, 23 meter. F is equal to 7.13 times 10 to the power of 5 divided by 23. So the force that you're supposed to get is 31,000 Newton. So 31,000 Newton is the answer. Second question A, define impulse. When this is about definition, remember just one thing, right? All the physical quantities, when they're being defined that way, right, there is only one exact answer. So the definition of impulse is force multiplies by time. You don't like to use the word multiplies here. You can put, you don't like to use the symbol multiplies. You can always put product of force and time. It is not a problem. Now B, Fig 2.1 shows a rocket and its exhaust gases. The exhaust gases are emitted from the rocket with a velocity of 1,400 meters per second at a rate of 2,800 kilogram per second. First part, show that the force exerted on the rocket by the exhaust gases is 39 kilonewton. State the equation that you use. Whenever they ask me to find force, right? When I see the word force here, I am going to use F equal to mama, because my mama forced me to study all the time, right? But the problem is we don't have acceleration. No problem with that. I'm going to do a little bit of modification. Acceleration here is being defined as the change of velocity per time taken. So I'm going to replace that m with v minus u over t. V is the final velocity. U is the initial velocity per time taken. Now, I want you to see this very carefully. This is kilogram per second. That is mass per time. So I'm going to put mass per time here and times with the change in velocity. That's it. Now I'm going to sub in the value. F is equal to mass per time. This is 2,800 or 2,800. V is with a velocity. I put 14, 0 minus 0. Therefore, I have 3.92 times 10 to the power 6 Newton. Make some modification. So it is 3,920 times 10 to the power of 3 Newton. Or you can round it off to 3,900. 10 to the power 3 is one of the prefixes, which is called kilo. So kilonewton. So we are done with this one. Now the second part, calculate the maximum mass that this force can leave from the ground. Ignore air resistance. I am definitely going to use the same equation. F equals to mama. So the maximum force is the one that I want to use. I want to use 3.92 times 10 to the power 6. It's not a problem. You can use 3,900 kilonewton is not a problem as well, right? So I'm going to calculate the mass and the acceleration leave from the ground. So that means you are going up from the ground. So the acceleration must be the acceleration of the free fall, which is 9.8. because you want to lift it up. Lifting or falling, that acceleration is related to gravitational acceleration. That's the tip for you. So the mass is 3.92 times 10 to the power of 6 divided by 9.8, 9.8, sorry, 9.8 instead of 9.81. So mass is equal to 3.98 times 10 to the power of 5 kilogram. 3.98 times 10 to the power of 5 kilogram. I put it in terms of three significant figures. Now, question number 3A. A car has a weight of 13,000 Newton. The car is supported by 4 tires. Remember, a car needs 4 tires. This is not bicycle. So the area of each tire. They didn't give you the total area of 4 tires. They give you the area of 1 tire, which is in contact with the road, is 0.016 meters square. Calculate the pressure on the road due to the weight of the car. Now, do you still recall the definition of pressure? Pressure is defined as force over area. So in this case, the force is the weight over area. Now the weight is given. The weight of the car is given 13,000 Newton. What about the area? So all the cars are on the road. All the tires of the car are on the road. So all the tires are in contact with the road. Don't you think so? Right. One area is 0.016, one tire. So I have 4 tires together. So I have to times 4. So the value that you get is supposed to be 203. I put it in terms of kilo times 10 to the power 3. You can put it in Newton per meter square, or you can change it to Pascal. It's not a problem. Newton per meter square is equivalent to Pascal. That is the unit of pressure, right? So 203, I put 203 kilo Pascal, or 203 kilo Newton per meter square. Now the second part, explain in terms of particles why the air pressure in the tires increases when the car travels along the road. This is definitely true. So I know that you have no car license now, just yet before you're sitting for your IGCSE, but you have bicycle, you ride on bike, right? So you can test this out yourself. You try to ride your bike, right, around your housing area, and then after maybe about 1 kilometer, and then you come back and you try to touch the tire of your bike. What do you feel? You can feel a little bit of hotness there. Why? Because when the car tires are in contact with the road, because the road is not smooth, definitely. This is not ice ring, remember? So the road is not smooth. There is a frictional force between the surface of the tire and the surface of the road, which frictional force gives rise to heat. So due to the heating effect and caused by the frictional force, the particles, the air particles inside the tire got the heat. Right, and when they gain the heat, they will gain the kinetic energy. They will move even further, even faster, even more vigorously, and they will collide with the inner wall of the tire more often. That is why the air pressure increases. So I'm going to write that down in word. So I will say that when car is moving, frictional force, acts, yeah, between surface of tires and road. So tires get heated or hot. You could say that frictional force causing heating effect. And bear in mind just one more thing, frictional force can only act when the object is moving, right? And okay, temperature of tires increases. When the temperature increases, what will happen? The air particles inside the tires gain kinetic energy. Air, because temperature is related to kinetic energy. If you remember, air particles inside tires gain kinetic energy. Air particles collide with inner wall of walls of tires more often, which increases the pressure. Right? That's the explanation. Now, B, a gas cylinder contains helium gas at a pressure of 2 times 10 to the power 6 Pascal, a volume of 0.026 meters cube of the compressed gas is released from the cylinder into balloons. Each balloon contains 0.015 meter cube of helium at atmospheric pressure, 1 times 10 to the power 5 Pascal. Temperature remains constant. That's good news. Calculate the maximum number of balloons that can be filled. Right. Another tips to be given here is that when you see there are two pressures and there are two volumes here, right? Always use this equation. P1 V1 is equal to P2 V2. This is called Boyle's law, no Girl's law. Oops, I also don't know why. So 2 times 10 to the power 6 times the volume, which is equal to 0.026, is equal to the second pressure. I will hold to the second volume first because there are a number of balloons, and each balloon can only be filled with 0.015 meter cube of helium. So I find volume 2, right, is 2 times 10 to the power 6 times 0.026 divided by 1 times 10 to the power 5, and volume 2, I got 0.52 meter cube. So 0.52, one balloon can fill in 0.015 meter cube, and I have 0.52 meter cube. All you need to do just to do your cross multiplication. I'll take 0.52 divided by 0.015, and I got 34.6 balloons that I can fill. But you know that I cannot get 0.6, right? So the maximum number of balloon that I can fill is just 34 balloons. So the answer is 34. The next one, question number 4. This is about specific heat capacity. Whenever you see the word specific heat capacity, there's only one equation, that is E equals mc delta T. C represents specific heat capacity. So specific heat capacity is the thermal energy or the heat required to increase the temperature of 1 kilogram of mass by 1 Kelvin. That is specific heat capacity. Now B, a volume of 0.0024 meter cube of oil is heated in a pan for 7 minutes. The temperature of the oil increases from 20 degrees Celsius to 180 degrees Celsius. Density of the oil is 910 kilogram per meter cube. Specific heat capacity of the oil is 2000 joules per kilogram per degree Celsius. Calculate the mass of oil in the pan. So when I see this kind of information, there's too many numbers here. I don't know what to use, right? And okay, I teach you. Start from the basic. You see density of oil is given. You are asked to find the mass of the oil and check. Oh, the volume of the oil is also being given. This is only 2 marks question. It wouldn't be that complicated. Start to use density is equal to mass over volume. So density of the oil is given, which is 910. Mass of the oil is the one that you have to find. Volume of the oil is given 0.0024. Therefore, do your cross multiplication. Mass is 910 times 0.0024. So the answer is 2.18. How do I know the unit of the mass? This is kilogram. So just put it in kilogram. So you can put it in terms of two significant figures, which is 2.2, right? 2.18 kilogram can also be accepted, or 2.2. Now, calculate the energy required to increase. When they talk about the energy, this is related to heat or thermal energy. When the specific heat capacity of the oil is given, you have to use E equals mc delta T. So the energy is E, mass of the oil, the one that I just calculated, 2.18. Specific heat capacity of the oil is 2000. 2000 here, 1, 2, 3. And the change in the temperature. So the final temperature is 180. Change in temperature, you just use the larger number, yeah, multiplies by a larger number, 180 minus 20. So your answer is 6.98 times 10 to the power of 5 joules. You could also put 7.0, but never put your answer as 7 times 10 to the power of 5 because that's one significant figure. So I put 6.98 times 10 to the power of 5 joules. Energy, the unit of energy is in joules. Now, calculate the power required to supply the energy calculated in B part 2. Power is defined as energy per time. Remember, energy is the one that I just calculated, 6.98 times 10 to the power of 5. And the time, this is 7 minutes. Remember, change your minute to second. 7 times 60, right? So I'm going to change it to second. 7 multiplies by 60. And use your calculator. You're supposed to get 1660 watt. Watt is the unit of power. Yeah, watt, right? So I put it as 1700 watt. 1700 watt. I round it off to two significant figures. Now, question number 5, A part 1, table 5.1 shows applications of regions of the electromagnetic spectrum. Complete the second column of the table with the region of the electromagnetic spectrum used for each application. Choose from the regions in this list, right? Gamma rays, infrared, microwaves, radio waves, ultraviolet. Each region may be used once, more than once, or not at all. Now, let us look at the first one. Oh, cancer treatment has been done for us. That's gamma rays. Bluetooth data connection. You can see some of the businessmen do put something close to their ear. That is Bluetooth. So Bluetooth use radio waves. Why? Because radio waves has the longest wavelength. It can travel far further. Optical fiber, the one that you use Wi-Fi at home, that's optical fiber. We use infrared. Infrared. And security marking, so to mark on your notes, right? So whether you're using the fake notes, right? That is called ultraviolet. Sterilizing food, you want to kill the bacteria on food, we use gamma rays. Gamma, this is gamma rays. And then wireless internet. Wireless internet, we are using microwaves. Microwaves. Yeah, that's the answer. And state the approximate speed of radio waves in air. Radio waves is one of the electromagnetic radiation which travels with the speed of light in air, 3 times 10 to the power of 8. Remember, all the electromagnetic radiation, right, travels with the speed of light in air as well as in vacuum. Now B, Fig 5.1 shows successive crests of a wave after a plane wave has passed through a gap. On Fig 5.1, draw 3 successive crests before the wave reaches the gap. This is the one that the waves that are being diffracted. They have already drew for you. You have to draw the incident wave. 2 marks are given because when we talk about diffraction, right? For diffraction, the wavelength is unchanged. So you have to make sure that the gap between this is called wavelength. It is similar to this gap that you're supposed to draw. Right? And you have to draw plane wave, vertical wave. So you draw 3 vertical wave directed towards the gap. That's it. Now the second part, Fig 5.2 shows a much wider gap. A plane wave of the same wavelength as in B part 1 is incident on the gap from left side of the barrier. So on Fig 5.2, draw three successive crests of the waves after the wave has passed through the gap. Now, since the gap is larger, right? So you don't have to draw that much of the diffraction, not much of the spreading will occur. Right, because only the small gap, every wave particles will be pushing every wave particle. So a lot of spreading will occur. But if the gap is too large, right, not much of the spreading, not much of the pushing will occur. So I would just draw almost similar to the incident wave. I draw three. One, okay, make sure that the gap are almost similar. Two, and then the third one here, maybe here. Okay, three. So when I draw these three, make sure that I said that there is also diffraction. Is that it's just that not much of the diffraction occurs, so it will curve at the end here. Okay, something like this. So this is the one that you have to draw. If it is less spreading, right? So yeah, and then please make sure that you draw arrows to show that this wave is being spread, right, towards the gap and after getting away from the gap. Now the next one, Fig 6.1 shows a full-scale diagram of an object O and its image I produced by a converging lens. The lens and its position on the principal axis are not shown. On Fig 6.1, draw a single ray, one ray to locate the position of the center of converging lens. Now, there are three rules in drawing a ray diagram. So when the principal focus is not being given, you use this one of the rules which stated that any ray that is passing through the center of the lens will just go straight without being refracted. So this is the ray that we are drawing. So from here, I know that the center of the lens is here. And the next one, they ask you to find, okay, or draw a line to represent the position of the lens and label the line L. So I'm going to do the labeling right now. So this is my ruler. I use a ruler. Okay. Draw a line. So I just draw a line here. Keep my ruler. And label this as L. And I'm done. B. Determine the focal length of the lens by drawing another ray on Fig 6.1. So you have to draw another ray to confirm the focal length, right? What is the focal length? Focal length is the distance between the center of the lens to the principal focus. Right. Now, since I have the lens here, so I will just draw another ray, which is this one. Okay, let me shift the ruler first. Horizontal ray. Okay, one of the rule stated that any ray that is parallel to the principal axis, horizontal towards the lens, will be refracted at principal focus. I'll just draw this out. Yeah, digitally, it might not be very accurate. So, okay, something like that. Here. So I'm going to keep the ruler first. Keep it. And make sure that you draw arrow for the ray diagram. So this is what we call principal focus. Principal focus is a point where all the rays will be focused to when it passes through a converging lens. So what is the focal length? Focal length is the distance between the center of the lens all the way, right, to the focal point. So that means this is called focal length. The one that I highlighted is called focal length. Now you can use a ruler to measure. The focal length that I measured was 2.1 cm. Now see, the object is moved 2 cm closer to the lens. 2 cm closer, that means very close to the lens. Okay, every point here has its own focal point, right? Principal focus. If you move 2 cm closer, so the object will be in front of the first principal focus. So this is like drawing a ray diagram for a magnifying glass. So the characteristics of the image formed by the magnifying glass are, first one, you might want to say upright. You might want to say virtual, and you might also want to say enlarged. right? We can accept either one of these two. Now, question number 8. Draw a circuit symbol for a potential divider. Now, you have to know that potential divider is used to divide the voltages, right, to a certain ratio by using resistors, by using the resistors connected in series. So the symbol of potential divider, you can draw just one resistor, something like this. It is just like variable resistor, but you put an arrow here because you want to, right, you want to alter the voltages or the PD. So this is a symbol of potential divider. B, fig 7.1 shows a circuit. Calculate the value of the V output, which is being connected to R output. Can you see that? When the value of R, which is variable resistor, the value of variable resistor is 3,000, 3 kilo ohm. Now, potential divider concept is just a ratio. So I'm going to use the ratio of V output over V input is equal to R output over R input. R input is related to total R. V output is the one that you need to find. V input is given total V, which is 6. R output is the one that is being connected to V output, which is 1 kilo ohm. Remember? So 1. I just put 1 here because both are in kilo. So R input, 1 kilo ohm. R input is the one that is related to total resistance of the circuit. Since potential divider concept can only be used in series circuit, all you need to do is just to add out all the resistances, 1 kilo ohm plus 3 kilo ohm. So you have V output over 6 equal to 1 over, I just cancel out all the kilo ohms, divided by 4. V output will be equal to 6 divided by 4, which is equal to 1.5 volt. So 1.5 volt is the answer. Now the second part, the value of R is adjusted until the current in the circuit is 1.7 milliampere. Calculate the charge that flows through the circuit in 300 seconds. Now the charge, I wasn't born to be good in memorizing all these equations, the formula. So I need to have my own way. Do you want to know how I memorize the equation of charge? You just need to kill it. That is how I memorize. So the charge, okay, the current is 1.7, but milli, you have to remember, is one of the prefixes, which is, if you don't like to put times 10 to the power negative 3, you could always change that to 10 divided by 1,000. Right? You have to change that milli to ampere. So time is given as 300. So when you use your calculator to do your calculation, you should get 0.51. And what is the unit of charge? It is coulomb. 0.51 coulomb is the answer. Now, question number 8a, fig 8.1 shows a wire carrying a large current. First part, fig 8.2 shows the square card view from above. On fig 8.2, draw 3 magnetic field lines that indicate the direction of the magnetic field and how its strength varies with distance from the wire. They give you 3 marks. That's a lot. So you could see that this is like current. To draw, whenever there's a conductor that carries the current, the conductor will have its own magnetic field, right? To determine the direction of the magnetic field of that current carrying conductor, we use our right hand grip rule. Just grip it, right? The thumb represents the direction of the current. The 4 fingers represents the direction of the magnetic field. Right, how do we do this? How do I know the current is into the card or out from the card? Very simple. I teach you. Very simple tip here. All you need to do is just to imagine an arrow here. Arrow. This is a tail of the arrow, right? When the arrow is coming out from the paper or from the screen, because the tip of the arrow is very pointy, what do you see? You could see something like this, a dot. When the arrow is going into the screen, what can you see? You see the tail of the arrow is like a cross. That also means that the current is into the card. So use your thumb, right hand. This is my right hand, by the way. Use your thumb, point into the card. Where are your 4 fingers? Okay, your 4 fingers will grip in this direction, which is clockwise direction. right? So we get that direction. All we need to do is just to draw the magnetic field. So how many magnetic fields that we have to draw? 3. Okay, fine. So the magnetic field that close to the current carrying wire will be larger. It is actually circular. I wasn't good in drawing. Circle. Okay, and it gets weaker when it is away. So your circle must be larger. So I'm going to draw here. Okay, I'm going to erase this first. Okay, draw a bit larger here. Okay. No, here. Okay, draw a bit larger like this. Okay, now the pattern of the magnetic field. Okay, 1 mark. And the magnetic fields are getting weaker when it is away from the current carrying wire. So that means the gap between all the magnetic fields that you are drawing would not be consistent. It is getting wider and wider. And the last mark will be given when you draw arrows, because magnetic field is a vector quantity. So these arrows outwards, clockwise direction, and we are done with that. Now the second part, the current in the wire increases and the direction of the current. You increase the current, but the direction of the current is reversed. Instead of current going into the card, current is coming out from the card. State how these changes affect the magnetic field. When the current increases, magnetic field is stronger. Magnetic field is stronger, right? Because the magnetic field depends on the magnitude of the current. And direction, because the current is the reverse, therefore the direction of magnetic field is also reverse. Instead of going clockwise, it will go anti-clockwise. Now, B, electricity is transmitted at high voltage. Explain why high voltage increases the efficiency of transmission even with thinner wires. I want you to highlight this. This is super duper important question that always been asked in paper 4. This is related to transformer. That is one of the reasons why we use step-up transformer to step up the voltage from the power station to a very high voltage. Transmit to your household. So if you want to answer this type of question to score 3 marks, I would prefer you to use equation. So I will use equation to answer this. Power generated by power station is equal to, okay, or you put a comma because I want to use a symbol. Station, I put P gen. P gen means the power P generated by the power station is equal to IV, where I represents current, V represents voltage generated by the power station, yeah? And then power loss, okay, I have to put forward here. Power, because this power must be transmitted through wire cables, right? Power loss in cables. Of course, some of the power will be lost in the cables, right? Which is P loss is equal to I square R, because the wires are being connected one after another. This is series, right? Where R is equal to resistance of wires. Right. Now, I want to make use of these two equations that I introduced here. Therefore, I put power loss is equal to, now, since I have already explained all the symbols that I use, I could use equation. Power loss is equal to I square R. Power generated is equal to IV. So power generated, oh no, I make I as the subject. So from power generated, I is equal to power generated divided by V. Sub into equation 1. So when I sub into equation 1, I have power loss is equal to power generated square over V square multiplies by R. So what can you see from here is that the resistance of the wire is always constant because we are using the same wires. So power generated from the power station is always constant at 230 volt to 240 volt. And R constant. So you have to tell us that. So hence, the power loss is directly or inversely proportional to V squared. That is why when you step up to a very high voltage here, the power loss could be decreased. So it is more efficient because less power loss, right? So that's the explanation. I hope you could understand. But if you face any difficulties, okay, or you have any doubts, okay, please do comment below. Yeah. Now, the next one, question number 9. An experiment directs alpha particles at a very thin sheet of gold foil. First part, most of the alpha particles pass through the thin foil in a straight line. State the conclusion about atoms from this observation. Of course. Why? Because the atom is mostly empty space, right? So there's nothing inside the atom. So atoms are mostly empty space. That is why, right? Empty space. Now, some of the second part, some of the alpha particles are deflected through angles less than 90 degrees, and a few are deflected through 180 degrees. State and explain two conclusions about the nuclei of the atoms from this observation. I would say that why alpha particles are being deflected, because there's something inside the atom which we call it as nucleus, and it's a very denser than alpha particles, right? It is very small, it is very dense. That is why the alpha particles that get close to the nucleus will be deflected. Right, so I would say that nuclei are very small and denser than alpha particles. Right? So explanation is that, oh, I have to put alpha. Okay, now no problem with that. Alpha particles that came closer to nuclei will be deflected more. Right? And also, conclusion 2, alpha particles and nuclei of the atoms are like charges because like charges will repel each other. If the nucleus inside the atom is negatively charged, alpha particles should be absorbed into the atom. So conclusion 2 is that, right? Nucleus or nuclei are positively charged. Right? So nuclei repel alpha particles at different angles. So that's the answer. Now B, a source contains a radioactive isotope of strontium. The isotope decays by emission of beta particles. The half-life of this isotope is 29 years. First part, state the change in the nucleus. Nucleus contain proton and neutrons. Remember that. Which occurs when a beta particle is emitted. So I have strontium. Okay, I just put it as X. This is a nucleon number. This is proton number. This is neutron number. So when a nucleus emit beta particles are fast-moving electrons. So what will happen is that the proton number decreases by 1, right? Whereas the neutron, because the proton decreased by 1, neutrons must increase by 1. So you could say that the number of protons inside the nucleus decreases by 1, or you could say that number of neutron, right? Number of neutron, okay, increase by 1, yeah, or change by 1. Now, the second part, the initial mass of this isotope of strontium in the source is 25 microgram. Calculate the mass of the strontium isotope that decays in 87 years. Since the half-life is being given, I would suggest you to use a table form. I didn't use equation because I don't quite like equations. right? That is more on probability. So I use table to help me to do it better. So I'm going to draw a table. It's not exactly like the table that you expected. So I will just keep the ruler. So this is what I draw. So I started the strontium at 25 microgram. So I just ignore, it's okay. You want to put microgram. So the time is equal to 0. So when this strontium decay to half of its initial value, which is you divide by half, you will get 12.5 microgram, right? This is the time is half-life, which is 29 years. And keep on decays until you get 87 years. So decay, okay, decreases by half again, you get 6.25 microgram. So this is 2 times the half-life because you divide 2 twice, right? So this is 2 times 29 years. You get 58 years. And then after that, keep on decaying. Decay divided by 2. This is 3.125 microgram. This is 3 times the half-life. Why? Because I have divided 2 by 3 times, right? So this is 3 times 29 years. You get 87 years. 87 years. Okay, let me put years here. Right. So I left with 3.125 microgram. So now look at the question. They ask you to calculate the mass of strontium that decays. This is what is being left. The one that is being decayed, right? Mass that decayed is equal to the initial mass, which is 25 microgram, minus the mass that you have left behind, which is 3.125 microgram. So you get 21.9. I put it in terms of 3 significant figures. 21.9 microgram. So 21.9 microgram is the answer. Right? If you have any hesitation or any problem that you're still confused, please do comment below. Now, question number 10. Fig 10.1 represents different positions A to H of the moon as it rotates around the Earth. State the position of the moon where an observer on Earth sees, first part, there is a quarter moon. If you want to see the quarter moon, you have to stand at A, right? The moon must be at A. Full moon, right? Full moon, okay, you see all brightness here. Full moon is actually E. Now, state the approximate time taken for the moon to orbit the Earth. Moon orbit the Earth is about 1 month. So you can put in days if you want, but I put in 1 month, easier. Right, so 1.0 month, because they didn't give you any unit at the time that you should put in. So you put in month, it is okay. Now, the average distance of the Earth from the Sun is 1.5 times 10 to the power 8 kilometer. First part, calculate the average orbital speed of the Earth in kilometer per hour. Orbital speed, do you still remember the equation? V is equal to 2 pi r over time taken. Because one complete circle is the circumference of a circle. T is the period. Now, 2 pi r is 1.5 times 10 to the power of 8. I'm not going to change that kilometer because the unit is in kilometer per hour. So divided by 365 days, because Earth orbiting the Sun is 365 days, change to hour. 1 day, 24 hours. So you're supposed to get 1.08 times 10 to the power of 5 kilometer per hour. So 1.08 or 1.1 times 10 to the power of 5. That's the answer. Now the second part, the speed of light in vacuum is 3 times 10 to the power 8 meter per second. Calculate the time taken for light from the sun to reach the earth. So I'm going to use the V is equal to distance over time. Speed of light is given 3 times 10 to the power 8. The distance is also being given, which is 1.5 times 10 to the power 8 kilometer. In this case, I have to change my kilometer to meter because my speed of light is in meter. So I times another 1,000. Divided by the time. Time is equal to 1.5 times 10 to the power 11 divided by 3 times 10 to the power 8, and I got 500 seconds. So 500 seconds is the answer. Now, the next one, question number 11, state the condition required for a protostar to become a stable star. If you want a protostar to become a stable star, that means the resultant force, the force, inward force, which is due to the gravity. Gravity is attractive force that pulling the star inwards must be balanced by the outward force. Outward force is the energy, is the pressure due to the fission process that occur. Right, so I've said that inward force, okay, due to gravity, gravity is balanced by outward force due to the process of fission. That's it. B part 1, define the Hubble constant. Hubble constant is the speed per, okay, so I'm so sorry. Okay, speed per distance which galaxies are moving away from where we are staying on Earth, from Earth. Now the second part, the current estimate for Hubble constant is 2.2 times 10 to the power negative 18 per second. State the equation which gives an estimate for the age of the universe. So I'm going to put Hubble constant is equal to V over D. Okay. V over D, where H naught represents Hubble constant, V represents the speed of a galaxy, and then D represents the distance moved from Earth. Now, the third one, calculate an estimate for the age of the universe. Definitely going to use this equation. V over D. Hubble constant is 2.2 times 10 to the power negative 18. And V, right, it is equal to, I just put 1 over T because this Hubble constant, not going to use this because I don't have the exact value, but this is per second, so per time. So 1 per time here. So the time is equal to 1 over Hubble constant, 2.2 times 10 to the power negative 18. And the answer that you should get is 4.55 times 10 to the power of 17 seconds, or 4.6, right? Times 10 to the power 17 seconds. So that's the answer. And that's the end of the discussion of February-March 2024 IGCSE Physics paper. So I hope you gain benefits from that. And if you need any the full answer in the PDF form, do chat me up, do WhatsApp me, do subscribe to my YouTube channel, do comment below. Thank you very much for watching, and I'll see you in my next video. Bye.